Erasing. Someone think of a question and ask me it. Oh, hey, video, by the way. All right. So questions. Yes?
4.19 from
I haven't got a clue what that is. You got to tell me what that is. I don't remember every single question. I'm not going to lie.
Consider the causal LTI system.
Yeah.
Response.
Yeah, let me see this. He's got it right there. Okay, 4.19. For particular input, the x of t is determine x of t. I bet they mean, oh, I see. We observed y of t, and then they want to find x of t. So we've got h of j omega. It's 419. It's, what was it? 1 over j omega plus 1? Plus 3? Okay, that's fine. And then we've got y of t is equal to, what is this? What's this?
E to the negative 3t.
Yeah, e to the negative 3t ut, and then plus e to the negative 4, minus, okay.
E to the negative 4 ut.
So e to the negative 3t minus e to the negative 4t. All right, ut.
Yep.
And then they say, find x of t. This is a great question. All right, so it's slightly different from what we've seen, because we're always saying, oh, if I know what y of t, if I know what x of t is, what's y of t? This is just going the other way around. So what do you think that we should do in this case if we wanted to go and find x of t?
Transform y.
Yeah, exactly. Transform y and divide by h. Because what we're going to have here is we're going to know that y of j omega is equal to h of j omega times x of j omega. And so what we're going to do here is we're going to just see then that x of j omega should probably be, x of j omega is going to have to be equal to y of j omega divided by h of j omega. So what is y of j omega in this particular case? Yes?
It's 1 over j omega plus 3 minus 1 over j omega plus 4.
Yeah, exactly. So we've got that, and so we can see here this is equal to y of j omega, and you should be able to just read that off by inspection, basically, because if you've got this thing times that little thing in your table says that this thing is going to go to that, and this thing is going to go to that. So that should be kind of by inspection. So then we're going to see here that this is. So 1 over this is j omega plus 3. So it's j omega plus 3 over j omega plus 3. I'm pretty sure you know what that is. And then you're going to have j omega plus 3 over j omega plus 4. Okay. And so what's this? 1. Right? I know that's not even a trick question. All right. J omega plus 3 over j omega plus 4. And so now from here, we're going to have to do a little trick. It's a trick we did in class the other day here. What we can do is we can just say, oh, well, this thing is actually equal to a plus b over j omega plus 4. So it's like a slight generalization of what we saw in partial fraction expansions. We just do it like that. And so what's one way that we could find a here? So it turns out I think a is going to be 0 in this case. Yes?
Can't we just use like 1 equals j omega plus 4 over j omega plus 4 and then subtract?
Yeah, exactly. That will work as well. That in this particular case, I think that's going to be easier because we're going to get j omega plus 4 minus j omega plus 3. Oh man, you're so right. Life got so much better, didn't it? And so j omega plus 4. And so then this thing is just equal to 1 over j omega plus 4. Awesome. And then, again, this is one we should be able to do by inspection. What would x of t be then in this case? E to the negative 4t times what? Yeah, exactly. This implies x of t is equal to e to the negative 4t times u of t. Yeah, perfect. So that's how we do that. That all make sense? And I'm gonna be moving over to the next one in a little bit. All right, questions. I'm also gonna take pictures of this crap just in case this video doesn't work good. And if I walk away without taking a picture, holler at me. Say, take a picture. Because like every now and then the video doesn't, work good. Like, cause this video may end up being terrible. In fact, I have a fairly high confidence that it is going to be terrible. All right. So, all right. Next question. Yes. 4.18. All right. Cool. What is 4.18? Tell me. Tell me now, or I will hurt people. Okay. Find the impulse response of that thing. Did you guys ever watch like Superman 4 and he says, "Where is the woman? Tell me now, or I will hurt people." It's probably my favorite movie of all time. Okay. So h of j omega is. This is a whack one. All right. This one's kind of tough. It's h of j omega is equal to, but it's going to have a lot of the properties that we have. Sine squared of 3 omega, sine squared of 3 omega over omega squared times cosine omega. And so what we're going to want to do here is we're going to want to do a bunch of product rule stuff, okay? So what is going to give us, so if we went and we're going to want to break this down into 3 components here. Sine 3 omega over omega. We're going to have that one, right? And then we're going to also do, the cosine. We're trying to find h of t? Yeah, we're trying to find h of t, so the impulse response. So we want to inverse Fourier transform this thing. And so we're just going to kind of want to think about this and say, okay, well, what are the things that are going to, what gives us something that looks like that? A rectangle function. And it's a rectangle function with what width? Where are we going from? -3 to 3. The only other difference is that there's going to be like a 2 here, either a 1/2 or another one. I don't remember what it is, so let's work that out really quickly. So I'm going to try to figure out what gets me to this thing. And then we're going to see that like once we have that, we just know that we're going to have to do some convolutions. And in the end, this is one that would be probably too hard to do in an exam. I'll just say that right now. But it does show us all the techniques. So let's just kind of go through the basic techniques. I probably won't work out the full answer because it'll take a while. All right, but let's work out this thing. So if we did, I'm just guessing it's from -3 to 3. So -3 to 3. A rectangle from -3 to 3 is going to have a Fourier transform that looks like this, right? That's our rectangle from -3 to 3. And this thing is going to be equal to 1 over j omega times e to the negative j omega 3 minus e to the, I got to have a minus up in there too when I'm doing that thing, times j omega 3. So that is plugging in the positive 3, that is plugging in the negative 3. And so we can see that we actually get, what's that constant factor that's going to come out? There's actually going to be a 2 up in here because when we have a sign, if you see the sign, there should be divided by 2j, so we needed to have 2 sine of 3 omega divided by omega. So that tells us that the Fourier transform, the thing that has the Fourier transform going to this is actually 1/2 times this, I'll call it this rectangle of t, where r of t is equal to 1 for t less than or equal to 3 and 0 for t greater than 3 in magnitude. Right. So so that's going to be that. So that's going to be that thing. And now what is going to give us cosine of omega? So what is going to give us complex exponentials? So cosine of omega, when we look at this, sort of one of the first instincts you should probably always have in life is to say, and there may be a table for this, I don't know, but I do know that this is true. that we can use our little rule to break this up as to complex exponentials. All I did is I took that cosine omega and busted it up as e to the j omega t plus e to the negative j omega t divided by 2. All right? So I took that in there. What is going to give us a complex what Fourier transforms to a complex exponential? Delta functions. So this is going to tell us that this is 2 delta functions. All right? And what value, what in particular, this is going to, what is going to give us, what has a Fourier transform that gives us delta? What has a Fourier transform that gives us e to the j omega t? What delta of what delta function?
The shifted delta function.
Shifted by what?
By t0.
Yeah, so it's actually just, well, sorry, not t. I needed to have a, it's actually, there's no t's in here. I'm sorry about that. It's e to the j omega minus e to the j omega. 'Cause there ain't no t's up in there, so there ain't no t's there. Guys got to yell at me when I mess up. Sorry if I'm going too fast. Okay, so this thing is going to be a delta shifted by 1, right?
Plus 1.
Well, it's minus 1, is
Plus
it?
1.
Yeah, it was going to be minus 1m plus 1, so it doesn't actually matter that much because
Oh.
it's the cosine.
Right.
So, but what we can see here is that it's actually going to be delta of t plus 1 is what's going to go up in there, because if we integrated negative infinity to infinity, e to the negative j omega t delta t plus 1 dt, this is going to pick off exactly the value when t is equal to negative 1, which is going to give you a positive j omega up in here, e to the j omega. And so we can see that this thing, the thing that Fourier transforms to this, is actually equal to, you know, it's the sum of 2 delta functions. So the thing is going to be 1/2 delta t plus 1 plus delta t minus 1. All right, so that's going to be our Fourier transform of that. And so then the final thing that we're going to have is going to be Can I just squeeze on in over here? So the final thing that we're going to have is it's going to be 1/2 RT convolved with 1/2 RT convolved with 1/2 delta t plus 1 and plus 1/2 delta t minus 1. All right, and so if we just quickly remember here, this thing convolved with itself, negative 3, this thing, if we convolve this thing with itself, it's going to give us a triangle function. And yep, so it's going to give us a triangle function that I believe is going to start at it's going to start at -6 and then go all the way up to +6, and then the overlap, the slope of it. So this thing is going to be, I'm going to have to divide the whole thing by 1/4. But the maximum overlap of this thing, if I did RT times RT, that's going to be an area of 6. And so the total thing, because I've got 1/4, it's going to be 4/6 or 2/3. So it's going to go up to 2/3. Is that right? Or 3/2 rather, 3/2. 3/2 starting at -6 up to here, up to 6. All right? And then what this thing is going to do is, what is going to happen if I convolve? So this is the convolution of these two things. Now what's going to happen if I convolve with this thing? What's it going to do? It's just going to shift it back. And this is just going to shift it forward. And so what we're going to have happen here is, it's actually going to go and we're going to be taking an average. So it's going to come up to the same exact value as it did before. It's going to, these things are going to end up, I'm going to get it a little bit wrong, but what's going to happen is it's going to go up from -6 to -4. There's not going to be, like, this is actually going to, one is going to shift back to -7, and then up at -5, they're going to kind of start overlapping, and these things are going to kind of, it's going to start off like this, and then it's going to go up faster. The slope is going to be by this. It's going to be, I'm trying to add graphs in my head, and I'm not going to be able to do that very well, but it is just going to be, this thing, you know, starting from -7 going up to 5 plus the thing that is starting at -5 and going up to +7, and you add those two things is the final result. But in the time that we have, I think we should move on. That's the basic idea. That is well more involved than I would give you. But that did actually show us a lot of the techniques. Most of these basic techniques, I think, actually are going to show up in some way. But that's a fairly complicated one. Yes?
How did you determine the 3/2 was at the top of the triangle?
Okay, yeah. So if I just took this thing, if I had this, if this was r of t and this was going up to 1, then what's going to happen is the area of this is 6. Okay, and so actually, so then the total overlap. So the maximum area that we're ever going to have whenever the things are overlapping is this times this, and it's going to be it's going to be exactly this function. So it's going to be area 6 is the basically the highest value that the convolution is ever going to take, and that's when you get the things completely aligned. Remember when we do sliding convolutions? So when we have the one that's sliding over exactly coinciding with the one that's fixed, then we're going to have area 6, and then I had 1/2 times 1/2, so I divided 6 by 4. Yeah. Okay. Next question. Oh, yes! Thank you. Man, you guys are good. What's that? Oh, and let me give us a label. That was like 618. 418.
That'll get people wondering.
Yeah, exactly. I was only just like 1 decimal point off. All right, yeah. Okay, wait. Oh no, my camera. What the heck? I don't want panoramic. That would be awesome, but no. All right. Wait. Let me do it again, just in case this was a terrible picture. And it may have. All right. Okay. Next thing that somebody wants to know about that's really bugging somebody. You can ask conceptual questions. You can ask me to solve problems. It doesn't matter. It's all up to you. It's a free country. So. 5.22f. Somebody got to tell me what that is. I got to move this over here. People go find this. All right. Well, I got to erase this thing anyways. 5.22f. Okay. No. That was one of your homework problems. Oh yeah. So some people did it correctly and got it marked wrong. So I'm going to show you 2 different ways to do it. And hold on, let me remove this. There's a lot of people in here. Right. Sorry. Right. And so many people actually did it right, and I think at least one person did it correctly and got it marked wrong because their solution was very different from the back of the book, the official answer guide solution.
What question again?
5.22f. Because somebody came to me yesterday and he was like, "What the heck? I got it marked wrong. This is totally right." And I was like, "You're right. It is right." So I gave him a point. That was you. Yes. Right. And so can I see the thing? Somebody? Yeah. Right. So it was x of e to the j omega is 1. Yeah. Please do. It is
e to the negative j omega minus 1/5
1/5
over 1 minus 1/5
Oh, I got that one right.
minus 1/5.
e to the negative j omega.
Yeah. All right. So there are 2 ways to do it. I'll first show you how the book did it, how the solution manual did it, and then I'll also show you how some other people did it. If you had the way the other people did it, then let me know. Send me an email so that later we can go adjust your grade. but I'll actually have to see your work. So the way the book did it is it busted it up into two terms that look like this: e to the negative j omega times 1 over 1/5 e to the negative j omega minus 1/5 1 over 1 minus e to the negative j omega. All right, times 1/5. All right, and we know that this is like one of our forms that we should be able to know what this is. We should know what this is basically by inspection. Again, this is one of those, we should know how to do it. So what we have for this one, this is e to the negative j omega. It was asking you to find x of n, all right? This is asking you to find x of n. And so this is n is equal to 0 to infinity 1/5 n e to the negative j omega n, right? Because that's that standard form. That is the Fourier transform of this thing right there. Should know that, all right? And then this is minus 1/5 times n is equal to 0 to infinity 1/5 to the n e to the negative j omega n. So those are two. So these are, because this is the Fourier transform that goes to that, and this is the Fourier transform that goes to that. And so what we can see here is that this thing, if we went and looked at this, this corresponds to this thing right here corresponds to the Fourier transform of 1/5 to the n un, right? And then this right here corresponds to a one-step delayed version of that, right? And so this thing over here, and so this is actually going to be minus 1/5. And then this thing over here corresponds to u to n minus 1, right? And so, so the final thing is actually that. That is one way of, times, yeah, 1/5 to the n minus 1. Yeah, so it's actually that. That's one way of doing it. Another way of doing it is to say, okay, well, that's actually kind of how the book did it. The book might have simplified it a little bit further, but that's good enough for my purposes. The book, but what some other people did was they said, well, geez, that is also equal to, and this is also completely valid, and this is before I said you could do this kind of thing in class, b over 1 minus 1/5 e to the negative j omega. And so what they did was they found this thing, and so what we're going to see here is this thing is going to be a Fourier transform of a delta of n plus b times 1/5 to the n u of n. And those are completely the same exact thing, and we can just figure out what the a's and the b's are. So let's figure out our a. We'll do that over here. So our a, I'm gonna call this thing v. Okay. So a is limit as b goes to infinity, b minus 1/5, 1 minus 1/5 v. What is that? Someone say it. I heard someone say it. Say it louder. What's that? -5. Yeah, it's equal to -5. Because what's going to happen if we just looked at this? If we wrote down, if we did the expansion, a of b over 1 minus 1/5 of b is equal to, if we went and did the expansion, if we let this thing go to infinity, this term is going to go away, so we're going to get left with that. And the b is just going to be equal to b minus 1/5, 1 minus v over 5 times 1 minus v over 5, evaluated at v equals to 5, which that's going to be, what are we going to get? This is going to be 5 minus 1/5, which that is some number. I'm pretty sure it's 24 over 5. But right. So a completely equivalent solution is this. Plus 24 over 5, 1/5 to the n. U of n. It's not obvious that these things are the same, but they are actually the same. If you went and like plotted them out, you'd see that they're actually the exact same thing. So if you did something like that, send me and the TAs emails and we can adjust your grade. Yeah, so, right. Did that answer that question? Cool.
Take a picture.
No, not yet. Oh yeah, let me write the thing. 5.22f. All right. Okay.
For that one that you just did, is this supposed to be two step functions or is the first one a delta?
No, that's actually a delta. Because what has a Fourier transform equal to a constant? The delta function. Yeah. So, yes?
How to choose the A value?
So the A value, what I did where is, everywhere, whenever we're doing partial fraction expansions, we don't want to like restrict ourselves to this kind of thing. We want to put in just a general number here. So I replaced the e to the negative j omega with some number, okay? And then if we're assuming that this is, if we're assuming that that expansion is true, and it is, you can go and check it, all right? Then I have something a plus b over this plus b, all right? And so I would have, let me go and write it a little up here. It's going to be a little ugly, but that's okay. So it's b minus 1/5 over 1 minus v over 5. If we assume that that is true, okay, then I know that if this is true, when I let v to go to infinity, all I'm going to get left with is this a term. So then all I have to do is let v go to infinity on both sides, and a is what's left over because of the thing in the denominator. And then the other one's just like standard partial fraction expansions. Yeah. Okay. I'm not taking another picture because whatever. You know, all right. More questions. Basic conceptual questions. Problem questions. Homework clarifications.
So how many depth?
How in depth, and then
I was gonna ask, like, do you have any questions that would help us for the exam?
I'd rather you do this. How in depth?
I was gonna say, how in depth do we need to know like even, odd, imaginary, real stuff?
Not very. I actually amended the
Yes.
thing because someone asked this on the forum, and I was like, oh yeah, that's kind of bullcrap, so I took it off. I mean, it's not bullcrap, but I'm not emphasizing it because it's like, yeah, it's a
So
bit
if we
much.
don't know how to do 4.7.
Yeah,
Okay.
yeah. Somebody asked that, and
Yes.
in response to that question in the forum, I took it off the thing. Yeah, and changed it in the list. Yeah, because yeah, that one I looked at, it was like, it seemed like, yeah, that seems reasonable, and it is reasonable, but it is asking a lot when you get down to it. So yeah. So, all right. Other questions? 4.9a. Let's see what that is. Alright. With the help of tables 4.1 and 4.2, find a corresponding expression for that thing. Ah, nice. This is a great one. Okay, hold on. Let me turn the thing. This is a fun question. This is closer in line with the kinds of stuff that you'll be seeing in the Right. No, it's fine. It's fine. I was actually, my original intention, and I took it off, was like there was going to be all these sort of, crazy Fourier transforms that arise in probability theory, and I was like about to put them on there, and I was like, and the gamma function is defined by this. How does this? And then I was like, that's so mean. I can't do it. So I stopped it. It was late when I made the exam. But I nicened it up. I got soft at some point in time. I'm gonna start from over here. It'll give me more room to work with. Although Which occludes more, here or there?
Wait.
It doesn't.
Okay, well, both.
They matter. What's that? You can't see anything. Can you see stuff?
No,
I didn't think so.
I think the board, that thing excludes.
Do you want me to like remove this?
Yes.
Just
Take it down, let's see it.
This is like such a bad
All of
design.
us sitting here with mirrors.
And that thing like doesn't even really work.
I think it's we're above maximum capacity. It's optimizing.
Don't call the fire department. Yeah. Okay, so all right, good. So this is 4.9a. This is what I call a good question. All right. So x of t is equal to 0 for t greater than 1, and t plus 1 over 2 for t less than or equal to 1. All right. Yeah, this one's great. Okay? Because what we can do is let's do x of t is equal to 1/2
I don't have the two.
x1 of t plus 1/2 x2 of t. And what you're trying to find is the goal. Find
Because it's 1/2.
x of j omega.
It's not 1.
And so when you see something that looks like this, that's a sum of stuff.
That's the Fourier.
You always want to be thinking
It's 1.
linearity. Let's break this up into simple ones. And let's do the easy one first. Okay? So where x1 of t is equal to 1 for t less than or equal to 1, 0 for or t equal to that, and for t greater than 1, and x2 of t is equal to 1 for t less than or equal to 1, and for t greater than 1. All right. Yeah, that's a t, or a very poorly drawn plus. Yeah, that's a t. Okay, we actually saw what the Fourier transform of this thing was. What is it?
Struggling.
What's the Fourier transform of x2?
What?
It's not just a sine.
Is that a thing?
It's a sinc function. All right? So x2 of j omega is actually 2 sine omega over omega. And we saw that before, right? We just did that one. All right, cool. Now, yes?
Where did you get the 2 from?
The 2, remember that 2 just showed up. We actually derived the 2 earlier in class.
Oh, so this is the formula.
That is the formula. Yeah, that is the formula. Because
Would we multiply it by 1/2?
then that 2 is going to go away. Yeah, the 2 is going to go away. All right. So, now, what is a simple way that x1 and x2 relate to one another? It's t. That's right. And yes, right, when we go to the Fourier transform. Yeah, it's true. All right. So x1 of t is equal to t x2 of t. So then now, how do the Fourier transforms relate? What's that? It's the derivative, right? So what we're going to have is x1 of j omega is equal to j times d omega x2 j omega. And so then, like that's a derivative. Yins can all compute that, I'm sure. We'll do it just because. All right. So it is equal to 2j times d omega times sine omega over omega. And so let's just remember our product rule. Low times the derivative of the high times the derivative of the low divided by low squared. So it's equal to 2j low d high, which is omega cosine omega, minus high d low, so it's sine of omega over omega squared. And so then the final answer is going to be, all right, we just add these two things up and then divide by 1/2, divide by 2. So x of j omega is 1/2 x1 j omega plus 1/2 x2 j omega. So then it's equal to j times omega cosine omega minus sine omega over omega squared, and then plus sine omega over omega. So there we are.
So the simplified version of that is just using the table to know that the derivative is always going to be 1 over j omega times the transform.
Wait, the derivative is, say this again, slow.
Like that 1 over j omega is equal to the...
No. So that's not the property we used, actually. So we used the property that t times something corresponds to derivative in the frequency domain, where you're thinking about the property of j omega times something equals a derivative in the time domain.
Right.
Yeah. You could actually use them, they would both work in some way, but this way is probably a little easier.
Okay.
Because I didn't multiply by like a j omega or anything like that, or divide by a j omega. I took a derivative of the Fourier transform. And that's from the rule relating, that's this rule relating t times something is equal to j omega times the frequency derivative. Yes?
What is the t less than equal to not what?
Oh, if the t was less than or equal to 2 as opposed to 1, so if we change the problem a little bit, yeah, then what we would do is we would still use the same kind of rule, but we would derive the Fourier transform of the constant, and then take the derivative of that thing. Because it's still going to be like a rectangle, right? We know the Fourier transform of a rectangle, so then we just take the derivative of that. We'll just have a different rectangle, basically. Yeah. So, all right, cool. Let me take a picture of that board.
That is simplified as you want it.
What's that?
Would that be simplified?
Yeah, I mean, you can't really get it that much better than that. Like, it'll go like only scarcely better than that. So, yeah. So, all right. I'll start erasing. Well, I'll erase the board. You think of stuff. Hey, you moved.
Yeah.
Right.
I can't see anything.
Right. When I turn around, I expect questions. Yes. Oh yeah. We'll see. Yeah. 4.13b. Okay. 4.13b. Ah, okay. So we got this thing. So is that thing periodic? So x of j omega. Can you read it off to me?
X of j omega
Yeah.
is equal to delta omega
Delta.
plus delta omega minus 5 plus delta omega minus 5. Minus 5. Sorry.
Minus 5
Yeah,
or pi?
5.
5. Is there a 5 and a pi, or a pi and a...
It's, no, you have it right.
Minus pi minus 5?
Right.
Okay. And then this thing, and h of...
H of t is the unit step minus unit step t minus 2.
Cool. All right, and so then it's asking you...
Is the convolution periodic?
Right. Is x of t convolved with y of t periodic. Oh yeah, x of t, h of t. X of t, h of t periodic. All right. So what we would see here, if we had something that was periodic, one of the things that we would see is that so each of these things. So let's just take a quick step back here. So this is what gives us the Fourier transform? Because what x of t gives us this 1, right? That's just constant. That's period with period 0 basically. All right. So we always put those when we have periodic functions. We can have constants there. That's fine. What is going to give us this thing?
The negative j by t.
Yeah, e to the negative j. E to the negative j pi t, and this is going to be e to the negative 5 pi t, right? Or e to the 5 pi t, right?
5 t, I guess.
No,
Yeah. So let's just work this out, okay? Because I'm trying to do it in my head and I'm failing. So this thing, all right, it is going to be. This thing, if we inverse Fourier transformed it, all right, it's 1 over 2 pi. And once we know how to do this one, we'll know how to do everything, right? E to the j omega t delta omega minus 5 d omega. Doing crap in your head is not suggested in the exam. All right, so this is going to pick off when omega is equal to 5. And we're going to be dividing by 2 pi. 1 over 2 pi, and then e to the j 5t, or e to the j 5. All right, and here's something that's kind of subtle, but if we add these two things together, they're not actually going to be periodic. This is periodic, this is periodic. Adding them together is not actually periodic because the least common multiple is like, there is no least common multiple of this, because this is going to give us 1 over 2 pi, because it's irrational, j pi t. All right, because this is irrational and this is rational, they're never actually going to have a common multiple. So it's not actually periodic. So what the question is going to kind of ask you is like, well, is this gonna pick this crap up? I'm guessing that it's not actually going to be periodic, mostly because of this thing, and then this thing is 1 over 2 pi, right? As the inverse Fourier transform of that thing is 1 over 2 pi. Okay, so what we can do here is we could go and look at this thing. Right. So what we are when we're gonna go convolve this thing, what it's actually gonna do, okay? We're gonna find our h of j omega, and our h of j omega. This thing, let's go and see how we can relate this to stuff that we know real good. So this thing is gonna pop up at t equals 0 and then pop back down at t equals 2. And this is actually just a rectangle function shifted by 1. So let's just call this r of t minus 1. And so then what we're going to have here is using the shifting property that we have. The time shifting property is going to tell us that this thing is going to give us e to the negative j omega times 2 sine omega over 2. Because we actually worked out the Fourier transform of this thing. Just, what's that? Over omega, not over 2, yeah. Over omega. Right. So that's our equal to h of j omega. Pretty sure I did my time shift correctly. Double check me if I'm wrong. Pretty sure I did that right. I always need to kind of double check, but I think that's okay. All right, and so what we're going to do is h of this thing times delta omega plus delta omega minus pi times delta omega minus 5. All right. So something cute's going to happen here. So when we multiply this by this, okay, what values of omega matter?
0 pi.
Exactly. But in particular, we're multiplying by this. What's the only value of omega that's going to change that could change the result?
0.
That's 0. So this is actually h of 0 times delta of omega. And when I multiply by this, what's the only value of omega that matters?
Pi.
Yeah. It's h of pi times delta omega minus pi. H of j pi, and then here same thing, only at 5. H of j 5 times delta omega minus 5. All right. So cool. What is sine of pi? 0. So that thing goes to 0. This thing probably doesn't. Sine of 5 doesn't go to 0. Sine of 0 doesn't go to 0. This thing, you do some L'Hopital stuff. Yeah. And so, yes, it is periodic. Because then we can see that that if we call this y of t, this thing is actually h of 0 times over 2 pi plus h j5 e to the j5t over 2 pi. So that is indeed periodic. And it's only just because of the so which bit, how I got from here to here?
Yeah.
Yeah. So I skipped one step, but let's work out this particular one because that's the most important one right now. So I've got h of j omega times delta omega minus pi, right?
Oh, I get that one.
Yeah, so we get that. And so it turns out that if omega is not equal to pi, that if omega is not equal to pi, then delta omega minus pi is equal to 0. And so the only value of omega where this could change the result is when the only value of omega where this could change the result is when omega is equal to pi. So that's why this thing, I can actually say, you know, because this, what's going to happen is that if we write it like this, we can write it as like, you know, this is equal to 0 for omega not equals to pi, and then h of j pi delta of 0 for omega equals to pi. And so we see that that's the only thing that really matters. And so I could have just as well said that this is equal to h of j pi delta omega minus pi. Get it?
No, yeah, I get that.
Oh, you get that?
I don't get the last line. What
The
happened?
last line.
What happened?
Okay, did you get why this goes to 0?
Yeah, no, I get that.
Okay, so all I did was I just plugged in, I found the inverse transforms of each of these things up in here.
Okay.
And then I just plugged that in. Because I found that the inverse transform of this thing is 1 over 2 pi. The inverse transform of this thing, well, doesn't really matter because it's getting hit by 0. And then the inverse transform of this, I worked out in gory detail,
Yeah.
was 1 over 2 pi e to the j5t.
So those are the time domain.
That's the time
And
domain.
then-
So I was finding, y of t. This is y of t equals to. Sorry, I guess I didn't. Maybe I just didn't write this.
Yes.
Yeah. Okay.
H of 0. These are constants.
Okay. Now I get it. I get
Yeah,
it. You were
yeah.
just. It was to me. It looked like you were mixing both the domains, and I was confused.
I sort of am, right?
Yes.
Because, this is the time domain representation. Yeah.
So what is
Yes?
it? So is it periodic?
Yes.
Why is that? How do we know that from the last one?
Tell me why it's periodic. Because the irrational term is gone. So we're just left with this. This is definitely periodic. E to the j5t. It's sine 5t plus j cos or cosine 5t plus j sine 5t.
Right.
And so then the only bit that varies is this. This is a constant. So it's a constant plus a complex exponential.
Shouldn't it?
Yes? Yeah, because this is hj omega. You plug a pi in here, you're going to get a sine pi over pi. The sine pi is 0. Yeah.
And the h is 0 over 2 pi, that's just going to shift the amplitude up and down.
Exactly. That's just going to be some constant. Yeah. Yeah, exactly. So it won't change the periodicity properties.
So that particular h0 to be equal to 2, right?
Yeah, it's going to be 2. Yeah. But some L'Hopital stuff. Yes?
So just
This is going back to.
Well, before I erase this crap, what number was this?
This is 4.13b.
4.13b. 4.13b. Yep. Question?
Yeah, this is going back to the different. I was just curious about the differences between the ways that we find derivatives. So there's one in that one you use equals j, or just j d over d omega times x2.
Yeah.
And then there's a different property where you multiply by j omega.
Yeah. So let's go through that.
Okay.
Let's go through that, and in particular say why you'd want to use one versus the other.
That would be
Right? Excuse me.
I'm just gonna do this right here. I gotta get my elbow out of the way.
I could take a picture.
No, you.
No, I'm just kidding. Yeah, you can. All right, cool. Thank you. Okay, so all right, we're gonna move this crap. So, sorry.
It's just like you're slowly getting more and more. It's like.
Am I encroaching on your
It's
space
fine.
more and more?
Works for
Just
me.
can't hold it up on the table. A lot of people don't. That's fine. It's just like it.
All right, so the question was one of sort of basic concepts here. When do you use the one thing? When do you use the one rule versus the other rule? And so the one is that you use frequency domain differentiation when you see you use frequency domain differentiation when you see something like, you know, x of t is equal to t y of t. Whenever you see something that looks like that. So in particular, if you ever see stuff that looks like, you know, if you ever see something that looks like that, and you want to take a Fourier transform of it, most people think, I'm going to have to do partial fraction expansions. You don't, because what you can do is you can just figure out, you know, this is just t times a constant, and then you take a Fourier transform with a constant, and then you, and then, because this is going to go to, if we go and do the Fourier transform of this, this is, under the Fourier transform, x of j omega is equal to j d omega y of j omega. So the main thing is if you ever see a multiplicative factor of t coming out, or t squared, or t anything coming out in the front of something, you know that you're probably going to want to use this derivative rule, because this will almost always be easier to first take the Fourier transform of whatever the t is showing up there, and then, you know, take the derivative of it. That's usually easier.
For generalized case, like if there is t raised to n, then it is j raised to n, right?
Yeah, exactly. Because you just do it n times. So it's the nth derivative times j to the n. Yeah. And then so that's when you want to use that. And then the other one where you want to use the actual where you want to use.
Oh, that's when it would be like x of t equals y prime. Or
Yeah, exactly. When you actually see a derivative in the time domain, then you wanna then you're gonna do, you know, if x of t is equal to dy of t dt, then we're gonna wanna, under the Fourier transforms, use our x of j omega is equal to j omega y of t. Y of j omega. And again, it's oftentimes going to be easier if y is something simple. A lot of times, yeah. So that's basically it. So if you can factor out a t, use this one. If you recognize that that's a derivative, or if it's told to you that that's a derivative, you use this one. Yeah. Other questions? Find some questions. I'll erase the other board. There's still room on that board. I'm going to keep that up there, possibly.
Yeah, 'cause you can see it.
Yes?
What would you note as like the key differences between the discrete time and continuous time transforms?
Yeah.
Like properties and stuff.
You know, the biggest thing is that, you know, you gotta have that the discrete time Fourier transform is periodic, right? That's probably like the biggest thing to know, right? And so like if you ever get something, you do a calculation and it's not periodic, then you've done something real wrong, right? Yeah. Yes?
Is there any equivalent to that derivative rule for discrete time?
Yeah. So there's a good one for you know, there's a good one for this one. Not so much.
Okay.
This one, it's not as clean. Yeah. So but for this one, yeah, I don't remember it off the top of my head. I can tell you what it is. Like it's a relatively.
I just know the tables didn't have one that was like that.
Yeah, I'm pretty. Yeah, because in the end, there's not really a. The closest thing they have is the differencing operation. So the closest analog they had would be x of n is equal to y n minus y n minus 1, and then it's a pretty simple one because you could just see under the Fourier transform x of e to the j omega is equal to y e to the j omega, and then minus the delayed version, so you're just going to get an e to the j omega y e to the j omega. So this thing collects out in front. So that's sort of the closest analog that you have in discrete time. And there is something like this that occurs in continuous time, a derivative rule. I don't remember the exact formula off the top of my head. It would take just a minute or so to derive. In terms of general, but let me go back to the other question before, if and when I do that. It's in the table. I don't know if it's that useful. You know, general differences. That's actually one of the big ones, actually, that they don't have, like, there's no natural, like, time derivative. Yes?
And just with clarification for the second one, the x is equal to y, can we, like, square that, so the second derivative?
Yeah.
Okay, so we can go down and it'd be j omega squared.
Yeah, exactly. Yeah, exactly. Yeah. Just the quantity squared. Yeah, exactly. Because in the end, you just apply that property over and over and over again. Yeah. Yes?
Do you have time to solve the 14th question?
Do I have time to solve the 14th question? Yeah. Why not? I mean, I have to leave by 4:30 so I can be in bed by 6, but that's okay. I'm kidding. It's not. It's creeping earlier and earlier. It's not that bad. But it really, literally is in life. Yeah. Today it was my dog at 3 in the morning. She started knocking on the door. She's like, "Hey, you gotta take me out." I'm like, "What are you talking about? It's 3 in the morning." She's like, "I don't care. I'm also hungry." And so, so she had to go potty and eat her breakfast at 3 in the morning for some reason. What's that?
Just slowly turning your family nocturnal.
I know. It's really weird. All right. So what was the question? 4.14. Okay, let's go for it. Can somebody show me what 4.14, or you read it? I'll just look at it and then you can read it off for me. All right. 4.14. Which one? Suppose we are given the following facts. I think that was listed as one of the ones not to necessarily do, because that's way harder than I would give you on the exam. Yeah.
Okay.
I'm pretty sure I didn't list that in the yeah.
There's the real analysis.
Yeah, that one's pretty hard. Yeah.
What was it to do? 12?
We did a very small amount of discrete time. Somebody asked a discrete time question before we go, because we've been really heavily on continuous
Because
time.
we all started on the practice problems and we started on chapter 4.
Yeah, I know. Right. We got a couple of discrete time ones in, not that many. Quickly, time me
I
one.
don't know which one looks good. Do we need to do 5.8? Which one do we need to do?
16, 19, 20.
16, 19, 20. That's it?
What? No, like all the same ones as before, but those are probably going to be the ones that we get stuck on. History is...
What about 16? Did we look at 16? Look at 16. Do you know that?
Oh, God.
That just looks gross.
I don't want to do that
I don't
one.
want to do that one either.
Can
Are we
you
going to
just
have to
not
do
ask
this one?
question?
Which one?
16.
That one.
Let me see it. Oh, that one ain't so bad.
Oh.
It's really not bad.
I don't know, I see see the sigma. Yeah.
I don't think I listed that one though. I may have listed it. Check if it's is it listed?
Which problem?
Oh yeah, I listed that. Let's do it. Okay. Yeah, that one's because that one it looks nasty, but it's not so bad. It's k is equal to 0 to 3.
Yeah.
It's x e to the j omega is.
And then it's the summation k 0 to 3, and then 1/2 k.
1/2 k.
And then over 1 minus 1/4
Yep.
e to the negative j quantity omega minus pi over 2k.
Okay. Omega minus pi over 2?
Pi over 2k.
Pi over 2k.
We have way more stress.
Alright. Cool.
I'm not exactly sure.
What is it asking you to do?
I don't know if k
I
is
can't tell if
multiplied
k
by
is
that or
in
divided.
It's I am pretty sure that is multiplying it. Yeah, that would make the most
It
sense.
should be k pi over 2.
Numerator.
Make it a
Yeah.
lot easier to read.
Yeah, I know.
Parentheses.
I know, parentheses. That's a badly set up question. Okay, let's see. Determine the value of alpha. G of n is equal to that. Oh, yeah. So, x of j omega is this, and qn is a periodic signal with period n. Alright. So, determine the value of n. That's a really hard question.
You assigned it to us.
Yeah, I mean, I didn't do every single question.
You said it wasn't that bad.
No, that's a really hard question. It's doable, but like in the time we have, that's going to be a nightmare.
So that's like not tested.
That is not testing. No.
Just go over,
Cool.
just go over 5.19.
5.19.
Since we know that'll come up.
Oh yeah, that's definitely along the lines. Okay, we got a better one. 5.16. When I look close at that, I was like, that's some hard crap. All right, like we could do it, but that's going to take us like 15 minutes probably. That's my guess, roughly. Yeah, read it out, please.
Yep.
Which one is this?
5.19.
Because this is much closer in line to the level of difficulty you're doing. If you could do 5.16, you'll really be good for the
This is
exam.
under the category of basic problems.
Y of
I know.
n.
What's that?
Y of n
Yeah, y of n?
minus 1/6 y n minus 1
Y n minus 1
minus 1/6 y n minus 2 equals xn.
equals xn. And then what's the question asking you to do?
Consider the causal.
Yeah, the causal difference equation.
Determine the frequency response h e j omega for the system S.
Yeah. All right. So for this one, you should be able to look at this and just kind of read it off, right? Because you should be able to see that when I plug in x of n was an exponential, I know that I'm going to get left with h of e to the j omega times 1 minus 1/6 e to the negative j omega minus 1/6 e to the negative 2j omega is equal to e to the j omega n. So just by inspection, you can use those properties that we've been using the whole time. So then I can tell you right now that h of j omega is just going to be 1 over this thing. So h of e to the j omega is equal to 1 minus 1/6 e to the negative j omega minus 1/6 e to the negative j 2 omega. So that's our frequency response. And then was there a follow-up to that?
The second is determine the determine the impulse response h of n for the system.
Yeah, determine the impulse response h of n. So what we're going to want to do here in this particular case is we're going to want to go write this thing down. Let e to the negative j omega equals to v, and then it's 1 minus 1 over v over 6 minus v squared over 6. All right? So we're going to write it like that. So we're going to take the roots, and let's go and see what the roots of this thing are. All right. So it's negative b over 2a plus or minus b squared minus 4ac. That's the quadratic formula. So negative b is 1/6 over 2a. So it's negative 1/3, right? Because 2a is that thing. Plus or minus b squared. So actually, what I'm going to do is I'm going to clear these denominators because that's terrible. I can't divide by 6 all over the planet. So it's going to be v squared plus b minus 6 is equal to 0. Yeah, we have that. And so we have v is equal to negative 1 over 2 plus or minus 1.
Yes.
Can we do it
It's
with a
just
calculator?
it's just plus 2 minus.
Yeah, but I don't own a calculator, so whatever.
Can we do a negative 3?
Yeah.
But
It's just plus
what?
3.
It'll
Plus
be
3 minus
It'll
2.
be
2.
3 and minus 2 because you factor
Okay.
out the 3 plus 3 and
3 and negative 2? Okay, great. Okay, cool. So, but that is, so this is going to be equal to v minus 3 and v plus 2?
Well, no.
v plus 3 and v minus 2.
All right, all right. So then if we divide that whole thing by minus 6, right, so we can say that this thing is going to be equal to 1 over minus 6 times 1 over v plus 3.
Can't we just evaluate it with a 6 in the numerator?
What's that?
Put a 6 in the
Yeah, just put a 6 in
Yeah,
the
we can just put
numerator.
a negative 6 in the numerator. Or, yeah, negative 6 in the numerator, b minus 2. Do some partial fraction expansions on that. And then, yeah. But in the end, what we're actually going to want to do here is we're not going to quite want to put it in that form whenever we do the this, because we're gonna want to get it into the form that looks more like this. So we're actually going to want to, you know, divide. We're going to want to pull this 3 out, actually. So then we're going to do 1/6 divided by 6 times v. So it's going to be 1 plus v over 3 times 1 minus 2 over v. So all I did was I pulled a 3 out here and I pulled a negative 2 out here.
Would we be able to go straight from partial fractions to that negative 6 over b plus 3 minus 2?
Wait. So the reason I want to do this is this is going to bring us to a form that's closer in line to our standard forms. That's why I wanted to get into Yeah, because I wanted to, because our standard form for this, like the thing that's in the table, looks something like this: a to the negative g omega.
Right.
So the reason that so what I did there was, yes, so this thing is equal to 1 over v over 3, 1 minus v over 2.
Oh, right. Okay.
Right.
I see what you did.
Yeah, you see what I did now? I just pulled that out so that I could get it. So I could get it into a form that looks like that, because that's the one that we have tables for. So did a little bit of work ahead of time to bring us into a form that's easy to work with. And so then what we're going to do is we'll do partial fraction expansions on this, which plus b over 1 minus b over 2. And then once we've done that partial fraction expansion, which I'm not going to do that just yet, I'll do that later, but we're going to see that our h of n is going to have the form, it's going to be negative 1/3, negative 1/3 to the n u of n plus times a times b times 1/2 to the n u of n. Because that's what we get from our, that's the table form. All right, and then we can find the a's and the b's by whatever partial fraction. Yes?
So are we going to pull out another negative out of one of those bottom packages?
Yes.
Because we have a negative 6 on top, so we're going to have to
Oh no, so the negative 6 on the top, there's a negative 6 that pulled out from the bottom.
from which?
From where?
So because you pull out a positive 3 here and a negative 2 here.
Oh, a negative. Oh, okay, sure.
Yeah, so it cancels out exactly. So that's why this is just true. Yeah.
I'm just
And
saying
so,
you should find.
let me just verify that indeed this is correct. So we get a 1, we get a 1/3 minus 1/2, that's 1/6. We get a 1/3 times 1/2, that's 1/6. All right, cool. And so then a
Yeah, I guess
is just equal to We get the A by just looking at this thing and letting v go to 3, v go to negative 3. So it's 1 over 1 minus v over 2, as v is equal to 3. And so this is 1, or v is equal to minus 3. And I don't know what that is, but because I can't do arithmetic, but you can do arithmetic better than I am sure. I can, yeah, v is equal to negative 3, and v is equal to 1 over 1 plus v over 3 as v goes to 2. That's what that is. So, those are numbers. I don't know what they are. You could work them out. It would take a minute approximately for me to work that out, which is a very long time. Yeah. Cool.
Okay. Quick question.
Wait, hold on. Let me take a pic. Yeah. All right. Yes.
So you showed us how to do this the other way using that property.
Yeah.
So like, if it just makes sense in my head, like when I take the derivative of that, and then you just end up with a square function, so a square root.
Yeah. That will work as well. It should give you the same result. It might look nasty.
It doesn't look anything like your result.
Okay. Right. So this thing.
Take that, and then this is the derivative.
Okay. Yeah. Oh. So you drew this out, and that is exactly this thing.
Yep.
The derivative of that is. Is one. Yeah. 1/2 of that thing.
1/2 of what we already know. That's the
Right. Yeah. So then you took the Fourier transform of that, and then you did the blah 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 blah. Yeah.
The Fourier transform of
Oh, so here's the thing. It's not exactly equal. That's why. So because what's going to happen is if you just did the running integral, it's just going to. If you did the running integral of this thing, it's just going to stay constant after this. And so the only way you can make it drop down is the the running integral is to put a delta function right here. That cancels, that makes this thing jump down instantaneously, and that's where that delta function that you need to put here. Because if you did the running integral of this, it's going to go whoop and then just stay constant. It's not going to drop down. To make it drop down, the thing that gives this as the integral is this minus a delta function with exactly equal area is that. So this thing has area, I think area 1 maybe. I think it has area 1. Yeah, it definitely does. And so it's just a minus a delta function right here. And so that minus delta function is going to cancel out with this thing exactly. And then you could go and it will work. It's just not. So you're going to get this j omega squared thing here.
No, I would have got up.
And then
I was like, okay, I'm gonna get up to
and then you need the delta function over there, and that's what's gonna. Once you have that delta function, you're gonna see that
But when they're done, I need to get
it'll actually work out. Yeah. Because you have that other term.
Right.
Yeah. So it's a little funky, but yeah, it's true. So. Question?
Quick question. Can we use our advanced calculators to do partial fraction squares? Sure.
Yeah, because now you're like,
Yeah.
I know one that forgot.
Right.
Thank you so much.
You're welcome.
You're in.